In many American calculus classes, there's a place where you get to after you've learned about the derivatives and how to take derivatives of all the various functions and so forth. And it's a section that we call related rates. Basically what it is a bunch of sort of contrived, made-up word problems. They give you an opportunity to practice taking derivatives and implicit differentiation. And in my experience, lots of students really don't like that section of the class or the textbook. In fact, when I was in graduate school, one of the first things I did before teaching classes was tutoring in our math learning center, which was down in the basement of the math building. And my first day I went down there, I had a 2-hour shift, and it was all Calculus 1 students, and they were all working on these related rates problems, and it was a lot of bad energy, a lot of frustration. So I don't know if I can change your opinion about these kinds of problems. I don't know that I can get mathematicians in America to not teach them so much or whatever, but maybe I can make your experience a little bit less stressful, at least by showing you how to do 1 or 2 problems. So since these problems are kind of contrived anyway, let's just really lean into it. Let's invent a made-up problem. Okay, so you're coming home from work and you see your house, and well, now you know it's made up, because if you're a millennial, then you don't have a house, right? You've got a student loan instead. Okay, but say you had a house, and then someone's tied a whole bunch of hot air balloons to it, and so your house is lifting upwards, and you'd like to go and chase it and get it back, but you know you're too far away. You've got your house somewhere up here, and you're standing 4 kilometers away, just looking at your house fly up off into space. And so what you can do is you can measure the angle that your eye makes with the horizontal. Let's call that theta. And what you can see is basically how quickly you're looking up, or at least there's instruments that can measure that. So let's say that at the point when the angle between you and your house is pi over 5, the rate of increase of that angle is 0.2 radians per second. In calculus, we like to measure angles in radians, and using time in seconds and distance in kilometers here. And so the question is, at this point, how fast is your house floating off into space? That's a related rates problem. And so you can see why, if you don't have lots of experience doing this, this might be frustrating. You might say, why am I doing this? But you really can do it. And every single one of these problems, I promise you, reduces down to nothing but an implicit differentiation argument or something thereabouts. So how can you do this? First, you need to figure out, in mathematical terms, what is it that you actually want to calculate. And if I call this distance, let's call it y. We usually label vertical distances with y. You want to find the rate of change of the distance from your house to the ground. So what you're really wanting is, what is y prime equal to at the point where theta equals pi over 5, and theta prime at that point is equal to 0.2. And the reason why these are called rates of change or related rates functions or problems is that you're given a rate of change and you want to find a rate of change that is related to it. In this case, you're given the derivative of theta, and you want to find a related rate of change, namely y prime. How are they related? They're related by this picture. And so let's go through it and let's think, what can we do? So how can we find like a formula or an equation that relates theta and y together? Well, I want to pause and think of maybe like the simplest thing that I can. And what I'm going to think of is, well, if I look at well, I've got two sides here, right? I've got the opposite and the adjacent side. So I may as well write down the equation that tangent, right? That's the function that deals with opposite and adjacent. So tangent of theta, that's equal to y over 4. And I'll just preemptively bring that 4 to the other side and put my y over there. Tangent theta equals y over 4, and just rewriting the equation like that. And so why do I say that it always boils down to like an implicit differentiation argument? Well, as soon as you write down the equation that relates the two variables, you're going to be wanting to take the derivative in order to find your answer. But this y prime could be a little bit confusing, because what variable are you taking the derivative with respect to? Well, the clue is in the way the problem is stated. It says, how fast is that house moving? Well, you want to measure that in time. So you actually want to take, if I put it in Leibniz notation, this is like dy dt. It's the rate of change of y with respect to time. And what am I taking the derivative of theta with respect to? Well, you can see here in the denominator, I've got time, I've got seconds. So that theta prime is really d theta over dt equals 0.2 radians per second. And here I've got an equation that you don't see a t there, you don't see time. And that might bother you. I don't blame you. But you can get through it with this idea of implicit differentiation. What you want to do is take the derivative of both sides of this equation with respect to time so that you can find your answer. And let me show you how to do that. So if I take dy dt, and I'll use Leibniz notation so that you can really keep track of the variables. So this is going to be the derivative of this function with respect to time. How do you do that? I want to use that chain rule. So the derivative of my outside function, that's derivative of tangent, I'm going to get 4 secant squared of theta, and now the derivative of the inside function multiplies by it to give me theta prime, or in other words, d theta dt. And so I'm asking, what's this quantity at the point where theta prime is equal to 0.2 and theta equals pi over 5? And I can just plug that in. So 4 times secant squared of pi over 5 times 0.2, whatever that quantity is. But that's now something that you can actually calculate. So what's happening here, you found an equation to relate theta and y. You knew that you wanted to take dy dt. And this implicit differentiation argument allowed you to do that, and then just plug in the data that you were given to get an actual number. So before I started recording this video, I actually calculated that out, and this was roughly equals to 1.22. And how can we properly answer the question? So how fast is the house moving? We should keep track of our units. We've got dy dt. Y is in kilometers, and t is in seconds. So based on just your recording of how fast that radiant angle is moving, you can now determine that your house must be slipping away at 1.22 kilometers per second. So that's at least one of these related rates kind of problems.